Now that you've had a chance to practice the electron configurations and orbital diagrams, there are, as usual, some rule breakers. I'd like to introduce to you two rule breakers, chromium and copper, and have us talk about why they are exceptional electron configurations. There are others, my friends, but these are the two that the AP board asks us to know. Therefore, I say memorize. Exceptional electron configurations of chromium and copper. In other words, they're going to be rule breakers. Let's take a peek at why they break the rule, filling their D sublevel and leaving their 4s partially filled. We'll write them into our note packs. So my note pack is opened up here to page 5, where the top of the page says exceptional electron configurations. Perhaps what I'd like to do is use some scrap paper, and that way I can write larger than the room given to me in my note pack. Let's take a look at chromium first. Now, chromium is a transition metal. Chromium is number 24 on our periodic table, so we have 24 electrons to write for. Let me, as we should, start out in the follow the rules. If we were to follow the rules for writing chromium, here's what it would look like. 1s2, 2s2, 2p6. 3s2, 3p6. 4s2, let me count. 2 and 2 is 4, 6 gets me to 10, 11, 12, 18, 19, 20. After the 4s, we begin to fill the 3d. We have 4 to place into that 3d sublevel. And remember, 2 2s 8, 10, 12, 18, 20, 24. So the superscripts do indeed count for all 24 electrons. If I think about, and I would just call this, these are known as the core electrons, more coming on that. The ones that are of interest to a chemist are known as the valence electrons, the outermost electrons that are available for bonding. So the 4s2 3d4 electron arrangement, if it had followed the rules, but we see that they're breaking the rules, and let's explain why. This 4s sublevel places 2 electrons in it. The D sublevel, now you know what, it just occurred to me, earlier lessons I were drawing boxes and now I am drawing circles. That's simply because that's the way I grew up drawing orbital diagrams. My teacher showed me to draw circles. Our text uses boxes. Some people actually use just dashed lines, and I've seen them in all different ways. So whatever you're comfortable doing, sometimes I fall back into an old pattern and draw circles. We place 1 electron into each orbital first. This would be the way had we followed the rules. But since chromium is a rule breaker, this is actually why. This is like saying in the 4th energy level, the s sublevel containing 2 electrons, yet there's an empty electron orbital down here at the end of the row. It's like making 2 siblings share a bedroom when there's an empty bedroom down the lane. What it actually will do is promote one to fill the orbital. So instead of having 4s2 3d4, we correct it. 4s1 3d5 is the exceptional electron configuration of chromium, promoting that electron from the 4s out to the empty orbital 3d. And like we said, the reason it wants to do that is it's just actually a more stable configuration, spreading out the electrons, taking advantage of the empty orbital. The other element we're asked to know is called copper. A very similar reason. Copper, who is number 29 on our periodic table, will have an exceptional configuration as well. 1s2, 2s2, 2p6, 3s2, 3p6. We would write it 4s2, 3d9, and that's going to give us the 29 electrons. Thinking about the arrangement here, here's the 2 and the 4s. The 5 equal energy levels for the d. Placing one into each orbital first, going back and giving a partner. Copper, if it followed the rules, would look like this, but we're being told in its exceptional configuration, it also promotes one of its electrons to complete the d orbital, fill all of those up, leaving just one in the 4s energy level. The correct configuration for copper would be 4s1, 3d10. The correct configuration for chromium, 4s1, 3d5. Structure, the shorthand way of writing an electron configuration, is just used to shorten the electron configuration so we don't end up writing with such redundancy over and over and over the same thing. What we do is take an inert gas. A lot of people call inert a noble gas. The noble gases are helium, neon, argon, krypton, xenon, radon. The noble gases live in the last column. Remember how every element is envious of the noble gases with their most stable configuration? We place the noble gas in a bracket, and that stands in place for all of the filled orbitals contained in the inert gas. The last noble gas you pass through before you arrive at the target element saves you from writing all of the electrons previous. Let me make some sense of this. Let's use a kernel structure. And when I say kernel structure, to me that means shorthand. For sodium, our first element for the example. Now remember where sodium lives. He's number 11. Third period, column 1, number 11. Third period, column 1. You know the last thing we are going to write for sodium is 3s1. Longhand, we would have to write it 1s2, 2s2, 2p6, 3s1. That gets us all 11 electrons for sodium. But here's an easier way. What's the last noble gas we pass through prior to getting to number 11? Sodium? Well, the last noble gas we pass through is neon, number 10. If I place neon into a bracket, that's the same as writing all 10 electrons of neon. That's the same thing as going 1s2, 2s2, 2p6. That adds to 10 electrons. Boy, that's shorter. The only other thing we have left to do is show that 11th electron that sodium configures. Neon in a bracket, 3s1. That's the kernel structure for sodium. In a bracket, neon represents the first 10 electrons. One more to get to sodium, 3s1. The last noble gas you pass through, and then just simply pick up with the configuration after that. Let's model another. Too many papers. Germanium. Germanium is number 32. Who's the last noble gas we pass through before arriving at germanium, number 32? Well, the last noble gas we passed through was argon, number 18. 18 is the last noble gas, argon. So in a bracket, I'm going to place argon, and that denotes the first 18 electrons. Now where do we pick up? Here's our target, germanium. We just passed through argon. Notice how we hit the fourth period? We go through the S block. And here's my target. I got to pass through the S block of the fourth period, 4s2. I then hit this row, scandium, titanium, vanadium, chromium, manganese, looking all the way down to zinc. This is the fourth period, but it's the third energy level of the D subblock. I got to pass all through those 10 elements before arriving at germanium. I'll denote those 10 elements, those 10 electrons, as 3d10. 2 more to go for germanium. Notice we go back to the 4p energy level. 2 more in there. We're going to end at 4p2. Argon in a bracket saved us from writing 18 electrons. 18 plus 2 is 20, plus 10 more is 30, plus 2 more gets me to the target of 32. Germanium's kernel structure: argon in a bracket, 4s2, 3d10, 4p2. Let's try silver. Silver is number 47. Who's the last noble gas you get to before hitting silver? Well, that's krypton, number 36. The last noble gas is krypton. So in a bracket goes krypton. And that saves us from writing the first 36 electrons. Where do we hit after krypton? Well, we hit the 5th energy level. Pass through the s block. 5s2. Notice how after a noble gas we always start with the s sublevel of the period we go to. Krypton finished row 4, so we start with row 5, the s sublevel. We're trying to get to silver. We're in the 5th period, but the 4d sublevel begins to fill. The d block is always 1 behind the period. 1, 2, 3, 4, 5, 6, 7, 8, 9 over in the d block lives silver. The last thing we would write, 4d9. Krypton, who is number 36, in a bracket, 37, 38 plus 9 gives us 47 electrons. The last example I'll work with you is tellurium, Te, tellurium, number 52. We have to write for 52 electrons, whose the last noble gas we pass through is again krypton. So again from krypton, after we fill krypton, that's like ending row 4, we pick up with row 5. 5s2 sublevel gets passed through. 1 behind the period, we have to pass all the way through the 4d sublevel. We go back to the 5th principal energy level for the p block. Tellurium is 4 over in the p block. So we said 5s squared, 4d10, 5p, 4 to get to tellurium. Krypton, who is number 36, 37, 38, 48, and 4 is 52. We've written for tellurium 52 electrons using the kernel method. We place a noble gas, the last one we pass through, into a bracket, and that abbreviates all of those core electrons. Those electrons are uninteresting to a chemist anyway. They're not available for bonding. It's those electrons past the core electrons that are interesting, allowing us to predict how atoms combine to form compounds. Pause your video lessons here and make sure the kernel structures are a comfortable skill.
We're going to talk about other trends, the first being atomic radius. We'll talk about ionization energy, electron affinity, and electronegativity. And we'll be doing so one at a time. So where we left off in the previous lesson was our Notepack page 13. We're picking up where it says periodic trends, and let's talk about the trends in terms of the size of the atoms, atomic size. And if we're measuring atoms in terms of how small or how large they are in comparison to one another, we'll first talk about how we measure. We realize that atoms themselves, or the way that they are composed, are mostly empty space, that we have to envision this electron area being more like a cloud. It's very difficult to measure the region of an area of probability. So what chemists have then decided is to measure the distance between the nuclei of two like atoms that are bound together. Think of those naturally occurring diatomic molecules. Horses need oats for clear brown eyes. Oxygen is one of those 7. In a diatomic molecule, when one oxygen bonds to another oxygen, it's very readily convenient to measure the distance between the nuclei, where those dense regions inside of an atom can easily be found. Once we measure how far the nuclei are from one another, we simply cut it in half and find the radius of the atom. Atomic radius is defined as 1/2 the distance between the nuclei of 2 like atoms in a diatomic molecule. The size of the atom from the nucleus to the outer edge of the electron cloud. Now, what are some trends we might discover as we think about periodic trends? This is a nice visual. This visual would be very helpful for you to sketch something similar into your notepad. And let's make some discoveries. Group trends. Describe the group trend as it's related to atomic radius. Groups, of course, go down. Columns are groups. What do you notice about the size of atoms as you go down the same column? Well, I agree. The atoms are getting larger as you go down the same column. Atomic size generally increases as you go down a group on the periodic table. Think about why. Each time we're moving down a column on the periodic table, we're adding energy levels. Additional principal energy levels, another ring around the nucleus filled with electrons. Each time we add an additional energy level, we've created a larger atom. Atoms get bigger as you go down a column. An atomic radii trend. Atomic radii, the size of atoms. Atoms get bigger as you go down a column. Why? Be sure you add that in your notes. Why? They get larger because you're adding additional energy levels. What do you notice about a group trend in terms of atomic radii? Periodic trends along the same row on the periodic table. Tell me what you observe as the periodic trend in the rows going across. I notice, as you do too, that the atoms get smaller going across, reading from left to right. Write that in your notes, that atomic size, the size of atoms, decrease as you move from left to right across a period. Why? That seems bizarre. Let's explain that in terms of drawing a little model here. If I think of element, I'll do lithium's row. Lithium right here. Lithium is number 3, mass number 7. So inside of my nucleus, I have 3 positive protons, 4 neutral neutrons. In my first energy level, I place 2 electrons, and in the second energy level, I place a 3rd electron. We understand to write that better. 1s2, 2s1 would be the electron arrangement in the quantum mechanical model, or the Bohr model. 2s electrons in that first energy level. Notice that 3 protons are attracting in 3 electrons. Compare that to the end of the row. Let's just do fluorine. Same energy level. Fluorine is number 9 with a mass number of 19. Thinking about what's inside the nucleus, I'm packing in more particles, aren't I? I have 9 protons and 10 neutrons packing the nucleus. The nucleus does contain more particles. The 9 electrons would place 2 in the first energy level. I have to get to 9 and 7 more in the second energy level. We now know to write that 1s2, 2s2, 2p5. That second ring truly has sublevels of an S and P sublevel. But more importantly, I can describe the trend. The trend brings me to a term called the effective nuclear charge. Our text uses a symbol, Zeph, the effective nuclear charge. 9 positive protons, 9 negative electrons. The more electrostatic attraction, the more those opposite charges attract each other, the smaller the atom becomes. 9 positives can pull in that second energy level closer and closer and closer to the nucleus. The more positive particles I pack in, the same energy level. Notice lithium has 2 energy levels. Fluorine has 2 energy levels, but fluorine has a greater effective nuclear charge. Effective nuclear charge is described as the ability of a nucleus Thank you. I got interrupted by the announcements. The greater the number of protons, the more control, the more ability it has to pull in the opposite charge. That these electrons are getting pulled tighter and tighter and tighter towards the nucleus because there's more positives pulling them in. A lower effective nuclear charge, fewer protons, it has less control over those electrons. There isn't as great of an opposite charge attraction. Atoms get smaller as you go across the row. Fluorine, the smallest atom in this column. Now I know it's hard to see on this diagram, but neon actually, when it fills its outer level, gets a slightly bigger diameter than fluorine. Fluorine, the most active non-metal, the smallest non-metal that's active. Cesium, the largest metal, the most active metal. Atoms get bigger as you go down because you're adding energy levels. Atoms decrease in size going from left to right because the effective nuclear charge of the nucleus pulls the electrons closer and closer and closer towards it. That increasing nuclear charge pulls electrons closer to the nucleus. Our book calls that ZF, effective nuclear charge. Let's talk about a second periodic trend, the term ionization energy. Ionization, let's try and kind of think about this root word ion. An ion is a charged atom that results from either losing or gaining an electron. Positive ions are known as cations. Negative ions are known as anions. Ions are charged atoms. Sodium, ion, +1 charge, it's a cation. Chloride, ion, it's a -1 ion. Ions are charged atoms either by losing or gaining an electron. So when we refer to ionization energy, very specific, it wants to measure the amount of energy required to overcome the attraction of the nuclear charge and remove an electron from a gaseous atom. The ease at which electrons are lost. Removing an electron. If it's easy, if that atom wants to give an electron away, very low ionization energy. If an atom does not want to lose an electron, more likely to gain, it would have a very high ionization energy. Ionization energy measures the amount of energy required to rip off an electron from its configuration. Now remember, electrons are being held in place by their nucleus. Just from referring to this other picture, how likely is fluorine going to want to lose an electron? If anything, fluorine wants to gain an electron to become like a noble gas. Compare that to lithium up above. How likely is lithium going to want to lose an electron? Well, very likely. Lithium wants to become a +1 charge. When lithium readily loses one valence electron, it has a very low ionization energy. Fluorine, who no way, shape, or form wants to lose an electron, would have a significantly higher ionization energy. How much energy it takes to remove an electron from an atom in its gaseous form is called the ionization energy. In my own head, I think, how easy is it to rip off an electron from an atom? Metals want to lose. Metals have a periodic trend of very low ionization energy. Nonmetals, well, they don't want to lose electrons. They want to gain to become negative. The nonmetals have very high ionization energies. Now, in terms of ionization energy, the first removal of an electron is known as the first ionization energy. The second ionization energy would be taking off a second electron, and so forth. What we notice is, in terms of a trend of ionization energy, we have a group trend. Let's be sure, pause if you need to record these. First ionization energy, removal of the first electron. Second ionization energy, taking off a second electron. We could talk third ionization, removal of a third electron, and so forth, removing an electron. Let's talk about the trends. In terms of a group trend, the first ionization energy generally decreases as you move down a group on the periodic table. As I go down a group on the periodic table, ionization energy decreases. I'm going to put up a slide. As I go down a group, ionization energy generally decreases. It is easier to remove an electron as you go down a column, because the outer electron is farther away from the nucleus. As atoms get bigger going down a column, think about it. Here's the outermost electron. There's the nucleus. Here's the outermost electron. There's the nucleus. The outermost electron. There's the nucleus. The nucleus loses control of that outer electron. This is a term we'll call the shielding effect. This outer electron of cesium is so far away from the nucleus, it is being shielded by all those inner energy levels. Every time we add an energy level, we're shielding the outer orbitals from the nucleus. And if that nucleus is positive, this outer electron being negative, if I take away its ability to attract, it's easier to remove that electron. The shielding effect. Lithium, this outer electron is much closer to the nucleus. It has very low shielding effect. Cesium's outermost electron is much more shielded from the nucleus, therefore easily ripped off. Ionization energy decreases as you go down a group. That's the same for any group. Because the electrons get farther and farther and farther away from the nucleus, they're more shielded from the effective nuclear charge, and therefore are much more readily removed. I wrote that in this direction. Because the size of atoms increases, the outermost electron is farther away from the nucleus and will be more easily removed. The farther out that valence electron, the more shielded it is from the effective nuclear charge. What about a period trend? Ionization energy, the ease at which we lose electrons. If we're thinking about rows going across our periodic table, The periodic trend are the rows going across. For representative elements, the first ionization energy increases as you move from left to right across the period. Remember, because the atoms get smaller as you move from left to right, it becomes increasingly more difficult to remove an electron. As we move across a row from left to right, the atoms become smaller. The smaller the atom, the more effective nuclear charge is going on. The greater the tightness between the electrons and positive protons in the nucleus. Couldn't spit that out. When atoms get smaller, they hold on to their electrons much more tightly. It's much more difficult to remove an electron from fluorine, very high ionization energy. Lithium very readily loses an electron, a very low ionization energy. Because atoms get bigger going down, the ionization energy decreases. Because atoms get smaller going across, they increase in ionization energy. The ease at which we remove electrons from an atom's configuration is known as ionization energy. Hydrogen helium, period 1, an increase in ionization energy. Lithium beryllium, boron carbon neon, oxygen fluorine neon. This is the period 2. A general trend, ionization energy generally increases from left to right, and it's the same trend. Generally speaking, from left to right, across the same row, ionization energy increases due to the atoms becoming smaller and smaller. Trends in ionic size. The size of ions. Top of page 14 in our notes. When atoms of metallic elements have low ionization energies, they will form positive ions easily. Metals become positive. By contrast, the atoms of non-metallic elements readily form negative ions. Nonmetals become negative. Metals are positive. Nonmetals become negative. When metals lose electrons to become positive, nonmetals gain electrons to become negative. What happens to the size of atoms when they lose or gain electrons? Let's talk about the trends. Positive ions are always smaller than the neutral atoms from which they form. Let's take a peek why. Let's just do a Bohr model. Let's do sodium. And I'll just do a Bohr model. Sodium's mass number 23, atomic number 11. Of 11 positive protons, 12 neutral neutrons, and we would go 2, 8, 1. Now it's an old planetary model. I know I would go 1s2, 2s2, 2p6, 3s1. When a metal loses an electron, and that's what we're doing, it loses that electron. To become positive, it's like erasing an entire energy level. Ions are smaller than their parent atom. Positive ions are smaller than their parent atom because we lose entire energy levels. Their outermost shell is completely lost. Ions, positive ions, are always smaller than their parent atom. Let's do the opposite trend. Negative ions are always larger than their neutral atoms from which they form. Let's take a simple fluorine. Fluorine with 9 positive protons, 10 neutral neutrons. The parent atom would arrange that as 2 electrons in the first energy level, 7 more in the second energy level. 1s2, 2s2, 2p5. If I take in an extra electron, which it wants to do to fill its outer shell, it goes from 7 to 8 electrons. It's gaining an electron. But notice what happens. 9 positive protons, 10 negative electrons. The effective nuclear charge is less. Adding negative charges to the same number of positives makes it a little bit more difficult to pull in that outermost shell. Because I add in an extra electron, that makes the cloud a little bit bigger. Negative ions are larger than their parent atom because the effective nuclear attraction is less for an increased number of electrons. Adding in electrons makes the atom get bigger. Losing electrons makes the atom get smaller. Positive ions are formed when electrons are lost. Negative ions are formed when electrons are gained.
The atomic size. The size of atoms increases as you go down a column as the valence electrons are farther and farther from the nucleus. As I go down the column, n equal 1, n equal 2, n equal 3, n equal 4. I'm adding shells as you go down the column, therefore atoms get bigger. And I say that because of the shells that we're adding. If n equal 1, 1 energy level, period 1. N equal 2, 2 energy levels, it's bigger. N equal 3, there's 3 energy levels. By the time we're done here, there's 7 energy levels. That's a massive sized atom. All right. Now, as you go across a row, atoms actually get smaller as you go across the row. And the reason? We add more and more and more protons inside of the nucleus, and more protons inside of the nucleus means they're going to have a greater pull to the negative electrons. So the more positively charged the nucleus is within the same row, the tighter the attraction. The opposite charges are pulling it closer, and atoms actually get smaller going across. Think of the trend this way as well. The tiniest nonmetal is fluorine. The massively large, 1, 2, 3, 4, 5, 6, 7, the massively large cesium, francium, atoms get smallest as you head towards fluorine. Atoms get biggest as you go down to the bottom left. I went into Google search and showed this visual for you as well, and it really is a nice visual to help you see the trends, how atoms get bigger as you go down a column due to increasing the number of electron shells. Atoms get smaller as you head across. Notice how fluorine is very small compared to the massively sized cesium. The trend? Atoms get smaller as you head towards fluorine. Atoms are biggest in the bottom left. Atoms are small. I should have drawn the arrow actually from cesium. This would be the direct direction. Atoms are biggest in the bottom left. Atoms are smallest in the top right. These are just going to ask us which is biggest. Which in the pair has the larger atomic radius, nitrogen or arsenic? And that secret just lies in the trend. Nitrogen versus arsenic. We'll look to see where they live first of all. Here's nitrogen, N, and here's arsenic, AS. They are residing in the same column. As you go down a column, atoms get bigger. Arsenic is further down in the same column. It is bigger. Same column, further down. Silicon or sulfur. Let's find where they live. Silicon or sulfur. Well, silicon, Si. Let's see if I can, here's sulfur and silicon. So they're in the same row. Atoms get smaller as you go across the row. So bigger would be the furthest left. Smaller would be the further right. So silicon is bigger than sulfur. Same row, further left. Fluorine and phosphorus. Well, fluorine we should know is the smallest of small. So right off the bat, I'm going to say fluorine, of course, we know to be small. I'm just trying to clean the screen. Here's fluorine, and we were comparing it to sulfur. Nope, phosphorus, my bad. Next door. Phosphorus is bigger. It's further down and further left. So two reasons. Phosphorus is bigger. It's further down and further left. And of course, I'm remembering fluorine is the smallest nonmetal. So always say this is going to be smallest, and you're comparing everything else to it. Rank the elements from smallest to largest. Smallest to largest. Potassium, calcium, rubidium, strontium. Potassium, calcium, rubidium, strontium. Oh, so they're kind of clustered right in this area. There's 4 that are clustered together. Biggest would be further down. Next biggest. The next biggest, so 1, 2, 3, 4. You know, these are kind of maybe hard to tell. This has an entirely different energy level. If you kind of consider these two, 1.9, these are just the element numbers. Those are kind of hard to tell, but it looks like with that first energy level, that's bigger than one down here with that second energy level. So I'm going to say the largest, rubidium, which is greater in size than potassium, which is greater in size than strontium, which is greater in size than calcium. And that grid, that's why I put this in here. It's so helpful to figure that out. The last of our periodic trends will be ionization energy. That's the energy needed to remove an electron from a neutral atom. How much energy does it take to rip off an electron from its neutral atom? The loss of an electron. So we notice that the smallest non-metal, fluorine, takes the greatest amount of energy to convince it to let go of its electron. The little fluorine atom is holding tight, tight, tight to its electron. It does not want to lose an electron. The smallest atom holds it the tightest. Therefore, it takes the greatest amount of energy to remove it. Now, the largest atoms down here, so far away from the nucleus that it's easy to pluck off an electron because they're not being held very tight by the nucleus. Largest atom holds the electrons loosely. So it takes low energy to remove it. The lowest ionization energy are the big atoms, bottom left. The highest ionization energy, that energy needed to remove an electron, the highest amount, the greatest amount of energy, are those atoms that hold the electrons tight, tight, tight to its nucleus, the small nonmetals, such as fluorine. And we can see a very similar trend between size of atoms, big down here, small up here, high ionization energy, low ionization energy. And the last of our chapter is just a little practice. I think I missed this down here. A little practice. Which of the elements has a higher ionization energy? Ask yourself in a different way, which is the closest to fluorine? Because that's the same answer. Highest ionization energy is the amount of energy that's the greatest to remove an electron. So we're asking yourself, who's holding that electron tight, tight, tight to the nucleus? Well, it's the smallest atoms, the nonmetals. Silicon or sodium? Silicon is closer to fluorine than sodium. It has a higher ionization energy. Carbon or silicon? Carbon is a smaller atom. It will hold the electrons closer. A higher ionization energy. Sulfur or fluorine? Well, fluorine is the strongest of strong. Nobody's stronger than fluorine, so therefore it's holding the electrons the tightest. Who's closest to fluorine between sulfur and fluorine? Well, that's fluorine. Which of the indicated atoms has the larger atomic radius? Atoms get bigger as you go down. We're adding energy levels. So number 2. Which of the indicated atoms has the higher ionization energy? Who's closer to fluorine? Who's holding the electrons tight? That's element number 1. It's closer to fluorine. We've done it.